there's not so much to say about this, or not so many results about this yet, but the excitement is the least I can share about this, and it's also an important dream, which is how we can contribute towards experimentally realizing quantum thermal machines that require quantum mechanics to capture their very functioning. This is a long and winding story, and time is short. So, and it builds on a mindset we have been developing over the last years, how thermalization comes about in the first place, where is also where this journey starts from. So, how do systems equilibrate and thermalize? After all, this is a feature that's seen ubiquitously in any experiment you can dream of, and obviously the notion of an ensemble, of an equilibrium state, is at the heart of any meaningful thermodynamic notion. Now, clearly, any closed system can never truly thermalize after all, but what can be true, and that's what generically is expected to happen, is that meaningful local expectation values soon take equilibrium values and stay there, in fact, for the overwhelming majority of times, and take the value of the infinite time average. That, I think Tiago has dedicated his talk also to that earlier this week. So there's a kind of a self-averaging, and that can be also made more precise, in that if one measures, the local expectation values will still fluctuate and wobble a little bit, but this wobbling, this variance, can be upper bounded by this quantity here, the 2 Rayleigh entropy of the infinite time average state, which is called the effective dimension. But that's really the effective dimension of the subspace that's being explored by this non-equilibrium dynamics. And one commonly expects this to be exponentially large, so that the state overwhelmingly looks like a thermodynamic ensemble and stationary for the overwhelming fraction of times. So that's at least the expectation, that's system becoming stationary. You can ask, how do systems become thermal after all? Well, and then one commonly invokes some reading of the eigenstate thermalization hypothesis that basically says that many-body eigenstates are expected to locally already look thermal to a very good approximation, and if a system equilibrates, tick, and if the eigenstate thermalization hypothesis is true, tick, then one finds thermalization and systems forming their own heat bath in the absence of any true environment. So that's the upshot of the logic of the commonly applied argument, but this is still a bit shaky in many ways. The eigenstate thermalization hypothesis is not proven, and even the equilibration problem is wide open, as Tiago has nicely emphasized earlier this week, as far as I know. And like the effective dimension even is a nice quantity somehow, but it's impossible to measure. It's a bit of an elusive quantity. It's also not possible to bound. So when do systems even come to rest after all, which is kind of a stupidly open problem in a way. So let's take a different take as our first problem of a kind. And let's start from the most basic notion of what ergodicity could mean in a quantum many-body setting as the weakest assumption of what ergodic could possibly mean in the quantum realm. So the minimum thing one can agree upon is that this is true, that generic eigenstates of a Hamiltonian satisfy what is called a volume law for the entanglement entropy, which means that if you look at a subsystem and look at this entropy, that this will in one way or the other scale extensively with the size of the block, regardless of any detail, whatever, but that there's some sort of a volume law in entanglement is maybe the weakest notion one can agree upon that an ergodic quantum system would feature. Obviously, the eigenstate thermalization hypothesis states something much stronger than that, and there's overwhelming numerical and also in parts analytical evidence that this is the case. So that's kind of the minimum agreeable, I would think, definition of what ergodicity could possibly mean in the quantum realm. Good. So slightly more precisely, we call it system entanglement ergodic if there is some lower bound that scales extensively with the size of the system and a function that depends on the energy in a reasonable fashion. This can be made more precise, but let's not be overly pedantic here. So that's kind of a minimum agreeable way of thinking what ergodic means in the first place. A couple of comments. So this is based on the 2 Renyi entropy, but that's taken for convenience. Any other Renyi entropy would also do the job between 1 and infinity. It's stable under time evolution, which is a nice feature to have, and it's precisely what many-body localization is not about. But it's a feature to be expected for any generic ergodic many-body system in one way or the other. That's great, but what does this mean for equilibration after all? And the answer is a lot. In fact, it all means equilibration. The thing is, using this basic and very agreeable property of ergodicity, one can look at overlaps of product states with these many-body eigenfunctions in certain regimes and finds that this is such a constraint of a skew form that the diagonal states must have high Renyi entropy from which one can deduce that the system very strongly and nicely equilibrates. For any state in the trivial phase, one looks at the dynamics and the system would nicely equilibrate in time, and one gets bound to the effective dimension here. So the logic is different. Like from just assuming the system is ergodic in the first place, one finds that the system must necessarily equilibrate after all. So from very plausible assumptions on entanglement ergodicity, a very strong form of equilibration follows. The logic is different, that you don't assume equilibration to happen and then you invoke some kind of ETH to show thermalization, but you assume something weaker than ETH and from which you already provably get equilibration, and it's stationary, kind of a convergence to stationarity in a very strong fashion without any assumption on the effective dimension. It's a kind of a nice way of, a fresh way of looking at equilibration after all. Now for non-interacting systems, something much stronger can be shown. Which is the following. So it's true for a very large class of initial states, whatever. They can be strongly correlated, whatnot. The only thing you have to assume is that correlations are short range, like in a gapped ground state of a gapped phase or high temperature state and so on. Very general. The Hamiltonians are rather special in that they are non-interacting, translation invariant, long range, but of whatever sort. They can be general, but a non-interacting, that is to say, quadratic polynomial in bosonic or fermionic coordinates. And then, indeed, one can show that systems not only equilibrate, but in fact they become Gaussian in time. That's something we already looked at like almost 10 years ago, that they provably Gaussify, but what was open over the last 10 years is how one can show that transport on the level of second moment happens, that has to happen for equilibration to appear in the first place. And that was kind of left open all those years that we just tackled not just a couple of months ago. And we asked, under what conditions do these systems actually show transport? And the cute answer is, except from like finitely many special points that can be characterized, it always happens. It's just completely generic behavior. So completely generically, one does find a convergence to a maximum entropy state given the constants of motion. It's a Gaussian state with all glory and fine print and bounds that if one looks at a subsystem, it would really in time, with a quantifier in time, converge to a generalized Gibbs ensemble in all beauty and glory as a kind of theoretical lab where one really knows and hammers down the problem in all glory and generality. For the connoisseurs, maybe that's relating to Thiago's talk. The machinery at the heart of it is the Kuzmin's theorem. It's kind of a cute statement on like arrows going in time and you look at the incommensurate dynamics, but maybe that's something to be discussed offline. So the upshot here is, this is a nice theoretical laboratory. Non-interacting systems gaussify and converge in time to generalized Gibbs ensembles. That's kind of a nice theoretical laboratory where one really sees how things come to rest, equilibrate, and generalize, thermalize with all time information, glory, rigor, and error bounds, how this locally happens, this being perfectly compatible with the total system being closed. So systems equilibrate. You have a fresh look at equilibration, and systems also gaussify once you have a non-interacting system at hand. Good. So there's kind of a fresh take at how generalized equilibration, thermalization equilibration comes about in a theoretical setting. So these ideas motivated us already some years ago to join forces with our friends in Vienna that have a beautiful quantum device in their lab that allows to probe such properties, such features under extremely nicely, precisely controlled conditions, asking how one can experimentally probe such thermalization dynamics with cold atoms on atom chips. What is this? These are kind of like BEC-type atoms on top of chips that are held at bay with suitable trapping potentials, and in the specific setting that they have in the lab, it would be like a 2-wire prescription that can be tuned in the tunnel coupling so that one, in the difference and some quadratures of the phases and the densities, one actually gets a very nicely controlled 1+1 dimensional interacting quantum field sitting there in the lab, from which one can do stuff which like probe in time under very precisely controlled conditions. And one can also measure the phase variables and high moments thereof to enormous precision. One cannot measure densities. That's annoying. I mean, one can measure densities, but not the canonically conjugate variable to phases. But one can measure phases and monitor things in time as a kind of quantum device, quantum simulator of field dynamics, probing these questions of non-equilibrium. And this we looked at in some ramifications. So one thing we looked at, for example, was what I just related to a couple of minutes ago, to see whether this kind of gaussification in time can be monitored for these interacting or weakly interacting quantum field systems in the lab, which can be quantified by suitable fourth moments gauged by the respective Gaussian second moments, and indeed one finds in time that the system would gaussify kind of as expected. So at first we thought, great, nice, we can see these things, but the second thought was, wait a minute, it doesn't really look quite as anticipated. And then we thought, yeah, good, fine, but let's see, what's the initial state? I mean, that's crucial. And then we thought, well, we don't quite know. We can only measure phases, but not densities. That's annoying. Well, is it thermal? But we don't know. We can only measure densities. Okay, but is it like, how's the entanglement dynamics? We don't know. We can only measure phases. Is there kind of quantum coherence going on? Can it be used for a thermal machine? We don't know. You can only measure phases. So at some point we got a bit angry, saying, look, we have to see what's happening here and find a way of looking into the system. Can we look at this thing and measure the missing quadratures? Like it's a harmonic oscillator when you can only measure ever x, but never p. You will never see any quantum feature after all. And the idea I'm mentioning is a very simple idea. So I'm actually a bit confused with time. My time says 15 minutes and this clock says 9. I keep it short nevertheless, but maybe I take my clock as a reference because the clock is... Yeah, but it kind of jumped a little bit. Anyway, I keep it shorter nevertheless, but I keep my time as a reference. So can you measure the missing quadratures? And the idea is super simple, but it's kind of nice how cutely it works after all. And the idea is very simple. The thing is, there are some points where you can tune the system to the non-interacting limit of a sine-Gordon model, which in a discrete continuous Fourier transform means in momentum space you have like harmonic oscillators that at their respective speed rotate in phase space with a known velocity. Right? I mean, what is x at some time would become p at a later time and so on. But for all momentum space modes at a given time, at a given speed, which you know beforehand, which you know because it's a non-interacting model. And then you make the whole thing a ridge prediction problem. So what you do is you go into the lab, you measure the system at different times, only phase-like information. Then you evolve, you make it a ridge prediction problem, you evolve the system for this multi-mode system in K-space, analytically, which you can because you've characterized the modes. It's a kind of a non-interacting model. And then one applies like compressed sensing type techniques or recovery techniques of finding the most plausible second moments that are compatible with the data at hand that satisfy the Heisenberg uncertainty principle as a semi-definite constraint. You make it a ridge prediction problem. You never measure densities, but you ever measure phases, but you see how behind the scenes the system is rotating, and then you can kind of predict what the densities are without ever measuring densities. It's a basic idea, but it works surprisingly well. When you first saw this, we were like blown away in that it shows like thermalization dynamics of a small system. It kind of equilibrates and goes down. But it's a finite system, so there's a kind of recurrence popping up later. That's the observed thing. What we did do at the lower end is a kind of prediction for a time window that shows no signature of finiteness whatsoever or recurrence. Using our ridge prediction idea, learning the hidden data that you cannot really measure directly, and predicting what will come later as a recurrence. And the system goes on, and you say there will be a recurrence, and whoop, the recurrence is there. But you never ever measure densities. It's a completely kind of ridge prediction of densities without ever measuring densities. It's a very cute way of looking into the system, of doing quantum measurements in this setting as a cold atomic quantum device. So quadratures can be measured, all quadratures. It's consistent with thermal initial state preparation, which is good to know. And one can look at questions at entanglement dynamics and all that, which is nice and cute. And it's good to have as a tool to understand what is happening in the system as a window into these systems. So that encouraged us even further. I thought, great, can you turn this? Now we have a tool, we can control it. We can look at quantum field dynamics. We can look at thermalization. We can look into the system, have a window into it. Can we turn this into a thermal proper heat engine, a thermal machine? And this is something we are just pursuing at the very moment, together with the Schmid-Meyer group, who has installed programmable DMDs, like digital micromirror devices that allow to program the potential in time in this setting so that you can monitor and control the system in a time-dependent fashion with outside control parameters. And together with our friends, like with Markus Huber group and Yasser Omar's group in Portugal, we are kind of setting up the operational primitives that are fully capturable within a kind of non-interacting limit of the primitives that you can use as control in this device seen as a thermodynamic heat engine. You can think of splitting. You take your guy, you ramp up the DMDs and you split up and you have a system and bath sitting there. You can merge and understand what's happening under merging. You can do non-equilibrium, truly entangling many-body time evolution as a kind of non-Markovian feature. You can do heating by having a small candle and following by non-equilibrium dynamics. And you can also compress adiabatically in a kind of way by which you can really think of an Otto engine with a compression cycle in this setting. So this will come out any time as a kind of roadmap of primitives towards realizing this as a thermal machine. This works beautifully. what is the next step, and that's what we are just working with, is to turn these primitives into proper, like, auto engines, heat machines that are conceivable, that demonstrate things like anomalous heat flow, for which we have first evidence that this works, of using correlations to have apparent heat flow in the wrong direction, non-Markovian dynamics, and so on, in a machine that's genuinely quantum in its functioning, where you need coherence and finiteness of baths to capture its very dynamics. 21 minutes, which brings me to the end of the talk. With like 3 minutes to meditate a bit on the, as a teaser, shall I say a few words before I conclude? I say a few words. So what I didn't speak about was the power of correlations, quantum thermodynamics. I say this to maybe interest people to grab me later. I'm actually quite keen on hearing your opinion, where the upshot is to use catalytic operations of having systems and baths, and operations that just make use of additional degrees of freedom sitting there. You have a joint operation with the property that they don't do anything to these degrees of freedom, but correlations can build up. Just additional thing. You can also reuse these degrees of freedom after all. And these operations are surprisingly powerful. For example, you can overcome like Jarzynski type inequalities in catalytic operations, having a positive probability of extracting work when looking at work distribution settings. I'm quite keen on hearing your opinion about this. One can do a single-shot characterization of the von Neumann entropy in a single-shot level, not asymptotic, but single-shot with implications for the third law. Maybe most cute, and that's the last point I'm making, is there's the common assumption that heat baths are baths. They're large to equilibrate and thermalize. But you can ask, what is the smallest environment you can have to actually equilibrate a system? Can it be big or very big or not so big? It turns out it can be tiny. You can, in 2 norm, exponentially nicely equilibrate a system in the number of degrees of freedom of a bath, independent of the size of the bath you equilibrate. If you find that surprising, ask me how that works. But very small baths can equilibrate many-body systems. Good. That brings me to my actual end. So, good. We went on a road here, on kind of an evolving dream. We started from ideas like good old friends of equilibration and thermalization, having a fresh take on notions of equilibration, turning things upside down with the Eisert thermalization hypothesis being the assumption to prove equilibration in the first place. We have a super general theorem on convergence to generalized Gibbs ensembles as a nice theoretical lab where one really knows these things once and for all in a limited, it is what it is, but clear, well-defined paradigm where one can really prove this in all rigor and glory. We have turned this into a setting where you can probe this in the lab with cold atomic devices, having a new window into this, see how this can be made a thermal machine, and this is something we are now very excited about, to use this to kind of not only talk about quantum thermodynamics, but really have something in the lab where we can really probe thermodynamic notions in a setting where quantum mechanics is really needed to capture the very understanding of the machine in its very functioning. And with this, I would like to thank you very much for your attention. I'm looking forward to the questions you might possibly have. Thank you.
Well, thanks, Jens. Thanks for that very interesting talk. Questions?